We know that the energy is given by 1/2 kx squared, and we know from this that k would equal 2u over x squared, and we're given that u is 0.0075 electron volts. If we change that to joules by multiplying by the conversion factor, we get the answer for k, dividing by the distance, which is 0.014 nanometers squared. This will give us a 12.2 Newton per meter constant. And now we can say that for part A, the angular velocity is the square root of k over m, which is the square root of 12.2 newtons per meter, over the mass, which is given as 3.82 times 10 to the negative 26 kilogram. That gives us a angular velocity of 1.79 times 10 to the 13th radians per second. For part B, the energy is given by n plus 1/2 h bar omega for n equals 0, 1, 2, and so on. So for two adjacent values, we notice that it's going to be just a difference of h bar omega, and plugging in the values of 1.055 times 10 to the negative 34 joule second for h bar times the angular velocity or frequency we just found of 1.79 10 to the 13th radians per second will give us energy spacing of 1.89 times 10 to the negative 21 joules, or 0.0118 electron volts, using the same conversion factor we used above. Part C, for the energy emitted by a photon, that's going to be the same as the energy between the spacings between two adjacent, and lambda then we can say is hc over E, or delta E if you want. So this is 4.136 times 10 to the minus 15 electron volt seconds times 3.010 to the 8th meters per second for the speed of light, over 0.0118 electron volt is the energy spacing, which gives us 1.05 times 10 to the negative 4 meters, or 105 micrometers. 105 micrometers would be in the infrared region of the spectrum.